Hello everyone, today we are going to learn about modified binary search. It is one of the most asked DSA question patterns in interviews, and that's why we are going to learn everything about binary search and what does this modified actually mean. So binary search is actually a way to eliminate half of the search space. So what this means is that you will have a search space and you will actually try to divide that search space and eliminate half of that search space. That is what binary search is. But then what is this search space? Search space is nothing more than elements that you are dealing with. Suppose you have an array. So you have 1, 3, 7, 8, and 10, like just say. So this is basically your search space. Search space is all the elements that you have at your disposal to actually use and figure out what you want to figure out. So here the search space is what? 1, 2, 3, 4, 5. We have 5 elements. So the search space is 5 elements. Simple as that. Now what the binary search aims to do is it tries to divide this search space in such a way that you can actually eliminate half of it, either this side or you can eliminate this side. That is what the main aim of binary search is. The main aim of binary search is not to find some element or find some value or do something. The main aim of binary search is to eliminate the half of the search space somehow. Because when you eliminate half of the search space, the remaining half of the search space is easier to search into, right? It's just less elements to deal with. And that is the only goal of binary search, eliminating half of the search space in some way. Now here we have used the elements of the array as a search space, but search space can be anything. It just needs to have element. You can simply have a set of 1, 5, 9, 8, 10, like these kind of elements. You can have a set and you just want to kind of divide that set into two parts and eliminate half of that set values so that your search space will reduce to the other half. So this search space is nothing more than a set of all the elements that we have in which we can search for the particular element or do the particular thing that we want to do. Let us try to understand the division of search space with the help of an example. Suppose that you have an array like this. We have one, and now we have a, like just say, target. Target is 10. Now we want to find out the 10 or whether the 10 exists in this particular array or not. We can go ahead and put a pointer here, p1. Then we can just check, is this 10? It is not 10, right? I can shift here. Here I will check here. Is this 10? It is not 10. Then again I will shift here. I will check 8. Is this 10? No, it is not 10. Then I will go here and I will check here. Is this 10? Yes, it is 10. Then I will say, okay, return true. We do have 10 in the search space or in this particular array. But as you can see here that if 10 was not here, if 10 was at the end here, if this was some other element, something else, right? Then what I will end up doing is I will go to this place, then I will go to this place, then at the end I will find the 10 and then I will return true, which will take around order of n time complexity, right? It's a linear time complexity, but we would like to reduce it because what if the array contains around, I don't know, 1 trillion elements? I mean, you will have to just go through all 1 trillion elements to find the element that you need, right? And at that scale, it becomes really important for you to somehow divide the search space and eliminate the part of the search space where you will simply not find your answer. So now the question is, how do you divide the search space? Because if I randomly divide the search space from here and then I say, okay, I'm going to eliminate the search space, how do I make sure that this particular 10 value is not going to be in this particular search space? That's the question that we are facing right now. And the answer to this question will be provided in the problem itself. So in the problem, you will have some kind of condition. It will be either a rule or a condition or some kind of situation that will help you to figure out whether this particular given 10 exists in half of the search space or not. So you will really have to read the question properly to figure out the rule, the condition or the situation that will help us to divide the search space in two parts and eliminate one of the parts. So here in this case, what is the rule? Well, the rule is very simple. We have a sorted array. And since it is sorted, we have this particular rule implicitly told to us that this particular element, the ith element, will be less than or equal to the I plus 1 element, right? The element at I index will be less than or equal to the next element. Simple. And that is a rule that we can use now to divide the search space. So how can we use this rule? We will simply have two pointers, L and R here, and then we will try to find the middle point. So L plus R divided by 2 equals to the mid. And right now the indices of these elements are 0, 1, 2, 3, 4, and then 5. So L is at 0, R is at 5. So 5 plus 0 divided by 2 is equals to 2, the integer division. It means here will be our midpoint, right? And we will check what is the element at mid. So we have 8. And then we can try to compare it with the 10, right? That is what we are doing. We are trying to compare this with the 10. We will see that 8 is less than 10. And now we will try to figure out whether we can use this condition or not. So right now we know that the 10 is greater than the current mid element 8. So it means the 10 will be on which side? On the right side, on this side, right? If 10 exists, it will have to be on the right side of the 8, because we know that the 10 is greater than 8, and if something is greater than 8, it will have to be I plus 1 index. And so what this also means is that this side, this entire side will not have 10 at all. And this is how we are able to use this rule to divide the search space and eliminate this particular part. Okay, and now all we have is this much. This is the part that we are going to search. So we will set the L to this 3 index, and then we will again find the midpoint. So right now the left is 3 and the right is 5. So 3 plus 5 is what? 8. So 8 divided by 2 is what? 4. Now the mid is here. So this here represents our mid. Right now the value at mid is 12. We will try to compare it with 10. We see that the 10 is smaller than the 12. It means 10 cannot be on the I plus 1 side. It means it cannot be on the right side, which means we use this particular rule to figure out that the 10 cannot be on the right side. It cannot be, which means it will have to be on the left side if it exists in the array. So based on this conclusion, we can take the R pointer and we can shift it to the mid minus 1. And now the R will be here. And now we can try to find out the mid again. So L plus R is what? Well, 3 plus 3 divided by 2. That is 6 divided by 2 is equals to 3, right? We found the mid element to be 3. So the mid element will also be here now, and we will cross it. Now we will check, is the current mid element equal to the 10? It is. Since it is equal to the 10, we will simply go ahead and return the index of this 10, that is 3. This will be the answer. Simple as that, right? So now do you understand how we are using these particular conditions or situations like sorted condition to actually eliminate the part of the search space in which we will not be able to find the current element, basically our answer. And in the same way, you will have some kind of rule, some kind of condition, or some kind of situation in each and every question that will actually help you to figure out which side of the search space can you remove and in which side you need to search. So you will really have to be on the lookout of this rule, condition, or situation present in the question. And based on this rule, situation, and condition, you will have to modify your binary search algorithm also. So here is the standard implementation of binary search. We have the left pointer at 0, right pointer at the last index of the array or of the search space, and we have the while loop which is going to run while L is less than or equal to R. Then we are here calculating the mid. Then this condition, actually L plus R minus L divided by 2, it is used for basically making sure that you do not go overflow. So it is possible that in language like C or C++, you will end up hitting the overflow issue. So in that case, this particular condition will make sure that you find the mid element without going overflow. But in languages like Python, you can simply do L plus R divided by 2. That's what you can do in Python. Now, once we find out the mid, we will have this if condition where we are checking if the element at a mid index is basically our target. If it is target, we will simply return the index m. If it is not our target, we will check if the element at m is less than the target, then we will use the rule that we got from the sorting condition. Since it is less than the target, we know that the target has to be on the right side of it. So we will update the left pointer to mid plus 1. We are not going to update to mid. We are going to update to mid plus 1 because we know that mid is not the target. So we don't need to update till mid. Otherwise, at the end, we are sure that the current element, the nums m, is greater than the target. So we are saying that R is going to be m minus 1 or mid minus 1. And then this while loop run until we find the element on this condition and we will return the element. Otherwise, at the end of the day, we don't find the element, we will simply return minus 1 or minus 2, whatever the question asks you to return. Now the question is, how will you modify this particular algorithm for different questions? And before we answer that, we need to understand where we can actually modify it. I mean, it's a very simple algorithm, it's a very small algorithm. So what are the points where we can actually try to modify it? Well, one of the points is this one. This is the condition. You can have L less than equal to R, or you can have L less than R. So we can have these two conditions inside of this while loop here. So we can modify based on this. Then the next place that we can modify are these conditions, these if and elif conditions, where we are trying to find the target. These conditions are right now written on the basis of the sorted list or the sorted array rule. But if you have some kind of other rule, these are the conditions that will change. Now let us try to understand how these conditions and these conditions will change based on other questions. So here we have a question. You are given an integer mountains array, it's an array, okay, of length n. So we have n elements in the array where the values increase to a peak element and then decrease. Okay, so the values are increasing and then simply decreasing. Okay, that's clear. Now we have to return the index of the peak element. Got it. So it means we will have something like this. So this is the visual representation of the data we will get. Suppose we have 1, then 2, then 3, then I don't know, 5, then 4 here, then simply, I don't know, like just a 2 here again, and then 0. So this is what is going to happen in the question. We will have an array like this: 1, 2, 3, 5, and then we have 4, 2, 0. So the question is very simple. It is saying that the elements in the array will increase till a particular position, and then after that they will decrease from that position. Now we have to figure out the peak element. So peak element here is what? 5. Peak element simply means max element, maximum element, right? So that is what we have to figure out. Where does this happen? Now currently I have 5 as the peak element in the middle, but it does not have to be in the middle. It can be at the end. It can be in the starting. How are we going to figure out which element is the peak element and return the index of that peak element? In the current example, we will end up returning 3 as an answer. And now this is where you will have to read the question properly, understand the situation, and you have to see what are the rules that you can use to eliminate half of the search space. Yes, you can go through each and every element and then find the maximum element. That is, yes, one situation. But in this kind of question, it will be told to you that you have to find out something that is not linear time complexity. You have to find out something like a order of log and complexity, which can only be achieved by binary search. So you are kind of forced to use the binary search in this kind of situations. So how will you be able to do this? You will have to read the question properly and see what is going on in the question. Here we are saying that the elements will increase till a particular element and then they will decrease. So what can we figure out about this particular element from this condition? We will be able to figure out that, okay, the left and the right element of this particular element will be less than it. So as you can see here that the 4 is less than 5 and 3 is less than 5. So it is one of the condition. The target element will be greater than left element and it will be greater than right element. Now what else can we figure out in the question? Well, if we look at the 2, we will realize that if the left node is less than it and the right element is actually greater than it, we know that the 2 is not the target, but the target needs to be in this direction, in the increasing direction. Why? Because the element before 2 is less than 2. It means we are on an increasing slope, on this slope. It means the maximum element has to be on the upper direction or the right direction of the array. So the other condition is that the element, if it is greater than x left and if the element is less than x right, then we know that the target needs to be greater than the element. Do you understand this thing? We have been able to figure out two conditions. Now the third condition is on this side. If we have 2 on this side and we look at the right is what? Less than 2 and the left is what? Greater than 2. So it means in the third condition we can say if element is greater than the right and element is less than the left, we know that the target is going to be less than the element, which means on this side. Because the third condition is signifying that we are on a downhill slope on this side of the array. And since we are on a downhill, it means the maximum element should be on this side. So now that we have these three conditions, we can go ahead and create our binary search algorithm. So now this is the new modified binary search algorithm because we modified the condition. We still have L is equals to 0, R is equals to the last index, and we have while loop as it is. We are still using the same L less than equal to R condition to run the while loop. We are still calculating the mid element just like we were doing it before, but here the conditions are changed. Right now, here we are checking if the element at mid index is greater than the element at left index, and if the element at mid index is greater than element at right index, that means we have found the peak element based on our first condition, and so we will simply return M here. Otherwise, if the element at mid index is greater than element at left index, and element at mid index is less than element at right index, we know that we are on a upslope. It means the peak should be somewhere here, right? That's why we will increment the L to mid plus 1. And in every other situation, we know that we will be on a downhill slope. So we will simply decrement the R to mid minus 1. And at the end, we are returning negative 1 just in case the input is invalid. But whenever the input is valid, this particular condition will end up returning the answer. So now I hope you understand how we can get the conditions from the question and use those conditions to modify our binary search algorithm. And that is literally all modified binary search is. Just a little bit of modified conditions and modified return statement. That's all. Now here is another example that will help us to understand modified binary search even better. So here we have a non-negative integer x and we have to return the square root of x rounded down to the nearest integer. Nearest means nearest on the left side. So if the answer is something like 2.89, we will end up returning 2. then the integer that we are going to return should be non-negative as well. And which is a valid point, because if I have something like 4, then we have two numbers, -2 and 2, as its square roots. So we are only supposed to return the 2 instead of -2. So the first thing that comes to mind is, what is the search space in this question? Well, the search space is all the elements from 0 to x. Yes, we have not been given an array from 0 to x like 0, 1, 2, 3 till x, but this entire search space has been given to us implicitly in the question, because we have to find out the square root of x, and square root of x can be anything from 0 till x. If the x is 1, the square root of x is also 1. It means the search space is going to be from 0 till x. Or you can remove the 0 and just say it is going to be from 1 to x. So all the elements from 1 to x are going to be in the search space. So think of this search space as an array that is starting from 1, then 2, then 3, and ending at x. That's what the search space is. Now, since we don't have an array, we have to calculate these kind of elements mathematically in the answer. So now let us try to get some conditions from the question. First of all, we have to get the square root of x. It means square root of x cannot be bigger than x itself. So we can have a condition like this: the square root of x cannot be greater than x. So the other condition that we can figure out is, if we take an element from the search space and we square that element, it should not be greater than x if it is a correct element. If the square of the element is greater than x, okay, it means that element and every other element after that, well, they will simply not be square root of it. So it means we can remove all the elements after this element. So this is an important condition that we can use. In the same way, the third condition is that if the element's square is less than x, it means the square root of x needs to be on this right direction. So we will safely ignore all the elements on the left side of the elements. So left side will be eliminated and right side will be taken. So now that we have these three conditions, we can try to create a binary search algorithm. So here is the modified binary search algorithm. The L is at 1, the R is at x, that is the ending element. Then we have the while loop, which is running while L is less than equal to R. Then we are calculating the mid. Then here are the conditions that we got from the question. So if the square of m, the square of mid, is basically equal to x, we know that the mid is actually square root. So we will simply return mid. Then if the square of m is less than x, we know that we need to go higher. It means we will simply update the left pointer to mid plus 1. And then in every other condition, we will simply reduce the r to mid minus 1, because we know that the m square will be more than x. And then at the end here, we are returning -1 in case the input is invalid. And that is it. This is the modified binary search algorithm. We are simply taking conditions from the question and using it here to modify our binary search to get the correct answer. That's it. So people face a lot of problem between deciding whether they should use this condition, left less than equal to right, or should they use this condition, left less than right. And the answer totally depends on what you are doing in the algorithm. If you are using left less than equal to right, you need to make sure that anywhere in your algorithm you are not setting left equals to mid or right equals to mid. If you are doing this, do not use this particular condition. Do not use, okay? Because if you are doing this, then you will end up having either left equals to mid or right equals to mid at some point of the execution. And from there, if you try to calculate mid again, it will give you the same pointers again, like the previous pointer, and that will cause an infinite loop. And that is not what you want. So if you're doing something like this, if you're setting L equals to mid or R equals to mid somehow in the code, do not use this thing. Do not use this thing, okay? This particular condition should only be used when you are using this particular while loop condition, so that you will not have any issues with the infinite loop. So it means you can use left less than equal to R only when you are doing left equals to mid plus 1 and right equals to mid minus 1. If you're using conditions like left less than R, then you can do left equals to mid or right equals to mid. The point of this condition is to make sure that you have some kind of ending point, and if you do not use them properly, you will end up in an infinite loop. That is like the other side of the blade. So yeah, this is all about modified binary search. Like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.